So in this part we'll start with where we have left in the last part. So now we'll start magnitude comparator. So the next topic in the combinational circuits which we have to discuss is our magnitude comparator. So as soon as you see the name as magnitude comparator, it means that a circuit which will compare the magnitudes of two numbers, okay, and give the results according the result. So if the result is like, if you compare two numbers, then the two numbers may be equal to each other, or one of the number may be greater than the other, or one number is less than the other. So based on this, your magnitude comparator will give you some outputs. So this is what you mean by magnitude comparator. So obviously you can see that a magnitude comparator will have in its simplest form, we will consider a single bit magnitude comparator in which there will be two inputs A and B, and these two inputs, each of them will be of 1 bit only, and then the outputs will be 3. Okay, so the outputs, 3 outputs, like if two of the numbers, if A and B both are equal, so it will give some, as I have told you, there are 3 cases which can arise. So based on these 3 cases, one of the cases will be correct and the other 2 will be wrong. Okay, so these are the 3 possibilities. So this is the general circuit which compares the magnitude of two numbers, just the magnitude. Okay. So we'll study 1-bit magnitude comparator, then we will study 2-bit magnitude comparator, and then 4-bit magnitude comparator. Okay, so because this is 2 to the power 0, 2 to the power 1 and 2 to the power 2. In this order we'll study. So let's see the 1-bit magnitude comparator. So the 1-bit magnitude comparator, if we talk about, so your 1-bit magnitude comparator is something, a black box in which we have to find, okay, what type of gates and how the gates will be connected. So this we have to find out, and the process will be same as we have done in our last few classes. So to find what is inside the black box, the way we will proceed is like we'll take 2 inputs. There are 2 inputs and there are 3 possibilities, L, E and G. A is less than B, so if A will be less than B, then L, if you put a LED over this 3 outputs, then when this 2 numbers, if A is less than B, then this LED will glow. If both of them are equal, then this LED will glow. If both of them, if this A is greater than B, then this will glow. Okay, so we are writing these outputs with A is compared with B. So if suppose I want to write the truth table for it, so we can write the truth table for it. So the truth table will look something like this. So 2 inputs are there and there are 3 outputs. Okay, when A is less than B, A equal to B, and A greater than B. So for each of these output, we have to like write a K-map or write some expression for this. So we'll see that how to write this expression for each of them. Now there are 4 possibilities for 2 numbers. So both of them are 0, 0. So then the 2 numbers A and B are equal. So you see this A equal to B, this output will become 1. Whereas the other two outputs, A less than B and A greater than B, will be 0. Whereas in this case, you can see that A is 0 and B is 1. So in this case, your A is less than B. So you see accordingly. Yeah, so this LED is high, or this output should be high in this case. Whereas in this case, A is greater than B. So this output is high. Whereas in this case again, the 2 A and B, both of them are equal to each other. So then this A equal to B is 1. Okay, so this is what it looks like. Now for each of this output, we can plot the K-map also, a 2 input K-map, so 2 variable K-map. Okay, a K-map with 4 squares in it, 4 cells in it. So we can do that as well, but rather than doing that, just by observation also we can write the expression. So you see, if you see this each one of them, so you see A less than B. First let's start with A less than B. So A less than B in this particular output column, you can see that the output is 1 for this particular case only. So you can write it here, A complement B, right? Whereas when A is greater than B, for that case the mean term which you should get is A B complement. So A B complement. Okay. So this is this corresponding to this A B complement. And if you consider this A equal to B, so it is nothing but a XNOR gate. Okay, XNOR gate is also called as equivalence gate. Okay, equivalent gate. So when both the inputs are equal, then only the output of a XNOR gate is high. So this is also called the equivalent gate or the equivalence gate or the XNOR gate. Okay, so you can call it anything. So now if you want to implement this particular magnitude comparator or 1-bit magnitude comparator, so the circuit which you can write for it, okay, before writing the circuit you can write the same thing with the help of the expression also, okay? And this will be helpful if you understand it properly here, then it will be helpful for you to understand the higher bit magnitude comparators. So for 1-bit magnitude comparator, if you see, if A is equal to 0 and B is equal to 1, then the case is A less than B. Okay, if A is equal to B is equal to 0, or like this, A is equal to B is equal to 1. So we have just written this truth table in the word form. Okay, so in this case, as I have told you, that is for equivalence case, you should always remember that whenever you have to implement this particular condition, that two bits are equal to each other, so better to use a equivalent gate, okay, or the equivalence gate. We should keep this in mind, because this particular thing will be very much useful in implementing the higher bit magnitude comparators and the cases in which these two bits are equal to each other. So for this case you can see that the other case, A is equal to 1 and B is equal to 0, in this case A greater than B. Okay, so G greater than. So this is what the conditions are. Now for this truth table or this expression, whatever you think is comfortable, whatever way you want to write and the way you are comfortable with, you can draw the logic diagram for it. So the logic diagram is nothing but it is very simple. So A and B are two inputs, and whatever expressions you got here, you implement that. So to implement A greater than B, so A greater than B is this. So we take A and B complement. So B, and this is B complement. After a NOT gate you will get B complement, and from here we are taking A. So it is, this gate will give you B complement A, right? And whereas this gate will give you A complement B. Same logic. And here this gate, you are using a XNOR gate, so this will give you A equal to B, equivalent. So this is how, if you implement this circuit, you can check it in the lab if you want. It will work as a 1-bit magnitude comparator. Okay. So inside the black box for this 1-bit magnitude comparator, this circuit should come. Okay. So this is a very simple explanation for a 1-bit magnitude comparator. Now let's move on to the other comparator. Again, the logic is same, that you have to make a circuit. You have to find what is inside this black box. When each of this word is a 2-bit word. Okay, so A is having two bits, A1 and A0, A0 and A1. So A0 is your LSB and A1 is your MSB. Similarly here, whereas the outputs are same as earlier, 3 outputs for 3 cases. L equal to means A equal to B, A less than B, and A equal greater than B. Okay. Now for this cases, if you write the truth table, then you can check the truth table. Again the truth table will be same. So rather than in the earlier case we have written it for 1 bit, now we will write it for 2 bits. So that is what the only difference is. So you see this both A1 and A0 are 0 0 and B1 and B0 both are 0. So this is the case when the two numbers are equal to each other. Okay. So you see, you have marked 1 in this column. Similarly for the other similar situations, you will see that for this case also you see this 0 1 and this is also 0 1. So 1 is coming in this column. Similarly for this case, so when you are 1 0 and this is also 1 0, so 1 is coming in this case. Again here you see, so 1 1 and 1 1, so 1. So for this all these 4 cases, A is becoming A is equal to B. Okay, equivalent gate will be used for this particular thing. How, we will see later. But for the other cases, if you check, let's say this case 0 0, when A1 is 0 and A0 is 0. So in this case you will check first the LSBs. So in this case you see that B0 is greater than A0. So if MSBs are equal, okay, we'll go to the MSB later on. We'll start checking. If you want to check any two numbers, we start checking it by, first if the MSB is same, we start with the MSB, then we find if the MSBs are same, then we go for the lower bit. So here as the word is of 2 bits only, so we'll check the lower bit. So if A1 and A0, A1 and B1 are same, then we see that where B0 is greater than A0, so this condition A is less than B satisfied. So you see the column, this you will put a 1 here. So similarly, if you write, you can write the outputs, all the outputs, you can mark where this 1 should come in the 3 columns according to the situation. Okay, you just check it. If you find any mistake, you just point me out. We'll correct it in the tutorial class or in the doubt class. So considering this, if you write the expression for this, so we'll see that if you can write the expression from this by solving it by K-map. You have to write 3 K-maps for each of the output. Okay, or otherwise if you solve it by K-map or by observation, the way we have done it for 1 bit magnitude comparator, if we follow the same procedure, then we see that when A1 is equal to 1 and B1 is equal to 0, okay, so this is the case that A is greater than B. So in this case, if when A is greater than B, so A is greater than B when if A1 is greater than A1 is equal to 1 and B1 is equal to 0. So if MSB is 1 of the number, so that number will be greater. So if MSB of this A word is greater than the B word, then you can see that A is always greater, then A is always greater than B. Okay, so for this 3 cases, A will always be greater than 1. The point is this. So from the truth table only, we have written this 3. So we have observed by writing the truth table that how we can write it mathematically in the words. So for this case, A is greater than B. So you write this expression as the corresponding hardware for this particular term you can write as, because this is non-complemented, so A1, whereas this is complemented, so B1 complement. Okay. Other way around, if A1 is equal to B1, when both are 0, or when both A and B, if A1 is equal to B1, okay, if both of them are 0, okay, or both 1 and simultaneously, okay, so in this case either A is greater than B, or in this case, so what is the case? The case is when your A1 and B1 both are equal, so either both of them are 0 or both of them are 1, and simultaneously A0 should be 1 and B0 is equal to 0. So for this cases you will find that A is greater than B. So how to write the mathematical expression for this? So it is very easy, because you can see an AND gate here and you can see an equivalent here. Okay, so equivalent gate. So for this case, equivalent gate you can write. So we have written an equivalent gate here. Okay, so A1 XNOR B1, and we have used here and for this, what is the case? A0. So A0 is non-complemented, so you put A0, whereas B0 is complemented, as you can see B0 is equal to 0, so you write a complement here. So for this case also, the output will be, the A will be greater than B. So for this 2 cases, the output will be greater than, A will be greater than B. So if you write them together, then you can see that the A greater than B will be the case when this logic is satisfied. You combine both of them. So combining both of them, you write the complete expression. So then it will become A1 B1 complement plus A1 XNOR B1 and A0 and B0 complement. Okay. So this expression and this expression we have ORed together because this OR is coming together. Okay, and ANDed this with this because the AND is here. Okay. So this 3 cases. Now A equal to B. So A greater than B we have seen. So we got the logic expression for A greater than B. Similarly, for A equal to B, the logic expression will be A equal to B will be the case only when both A1 and B1 means A1 is equal to B1 and A0 is equal to B0. Okay, both of them are 0 or both of them are equal to 1. So in this case, you can write the logical expression as A1 XNOR B1 and A0 XOR B0. So AND is used here. So this AND. Now for the third case, the case when A is less than B, so again there will be these possibilities, so you combine them together. So the possibilities are like this: if A1 is 0 and B1 is equal to 1. So you write this expression. So in this case A is less than B. So it is written as, because this is non-complemented, so B1, and this is complemented, so A1 complement, right? So for this case, or the other cases, when A1 is equal to B1, both 0 or both 1, and simultaneously A0 is equal to 0 and B0 is equal to 1. So for these cases, you can see, for these two cases, A is less than B. So how to write the complete expression? You combine them with an OR gate. So you combine this B1 A1 complement, which is this term, plus, so OR this, and A1 XNOR B1, so this and this term. Okay, so you see we have written this. So to implement this particular thing, a 2-bit magnitude comparator in the hardware, we have to implement these three expressions. So this expression we will implement, this expression, and this expression together. So let's see how we'll do this. So 2-bit magnitude comparator will look something like this. So these are our A and B. So we also assume that B complement is also present. If it is not, if you don't assume, if you assume that B complement is not present and only A and B are there, so use a NOT gate also. Okay, you can use a NOT gate. So if suppose for time being, if I consider that A and B bar both are, A the variable and its complement, okay, for all the 4 variables A0 A1 and B0 B1 are present, then you can write the expression like this, okay, a general form. So this is the gate for, you can see very easily that when both of them are equal, you have used the equivalent gates, okay, XNOR gates, and you have ANDed them together, right? And here in this case you can see that this is A B1 bar and this is A0 B0 bar, and you have ORed them together. Okay, so this is the same expression which you got earlier. Okay, so A greater than B. And for the third case, you take this as the input. Okay, so this input you are taking your because this one of this term, this coming here in this case, okay, you can see A1 XNOR B1. So A1 XNOR B1 is this term, so that is why it is taken from here. So this is coming, this is a 3 input AND gate, so this term is going here also, whereas this term is also coming here in this gate. Okay, so this is why. Now you AND them together and you OR with this, so then you get A greater than, A less than B. So if you implement this hardware, it will be useful to implement your 2-bit magnitude comparator. Now let's move on to the another magnitude comparator, which is a 4-bit magnitude comparator. So we'll follow the same procedure, following the same logic. You can implement a 4-bit magnitude comparator. For a 4-bit magnitude comparator, I have not shown the truth table because it would have been very long to show. It will not. We cannot show it on the. It will be difficult to show it on this one slide. So that is why I have not shown that this truth table. If you want, you can write that truth table. But if rather than writing the truth table, if you write the expression the way we have written it for 1-bit and 2-bit magnitude comparator, following the same logic, if you write the expression, then you can see that it will become something like this. So A is greater than B for this cases, when for your this cases. Okay, so if A3, because you see now here we have to compare 4 bits, so A starting from the A3 MSB, so A3 B3 will compare, then we'll compare. If A3 and B3 both are equal, then we will see A2 and B2. If A3 and B3 are equal, A3 and B3 are equal, also if A2 and B2 are equal, then we will go for the lower bit. Okay, so this is what the procedure is. So first we'll check, we'll start with the MSB. So if A3 is greater than B3, then the case will be A3 B3 complement. But if A3 and B3 are equal, and if A2 is 1 and B2 is 0, then in that case, this particular case can be implemented with this hardware. So it is XNOR A3 XNOR B3 and A2, okay, non-complement, and this is complement, so B2 0, B2 complement. And the other case when A3 and B3 are equal and also A2 and B2 are equal, but if A1 is 1 and B1 is 0, so in this case you can implement again with 2 XNOR gates and this term. Now we'll see the third case when A3 and B3 are equal, A2 and B2 are equal, and also A1 and B1 are equal. So the last bit we will see, which is our LSB in this case. Now we'll check the LSB. So the LSB, if A0 is greater than 1, A0 is equal to 1 and B0 is equal to 0, then we can see that A1, that A is greater than B. And to implement this particular thing, whole thing, okay, you can write the expression for this as well. So this expression you write the similar way you have written, following the same logic, you can write the expression for this particular case as well. Now if you combine all of them, then we can see the total expression for a greater than b case will be something like this. So this plus this, you can see this term here, then this term here, okay, all of them are ORed together, then this term, so this is here, and for this case the term will be here. So rather than repeating it 2 times, I've just done it single time, and the a greater than b case will be this. Similarly, if you see the other cases following the same logic, you can write the cases for a equal to b and also a less than b, and if you implement them together, then you can see the circuit will look something like this. So for a greater than b, these are the cases. So we have seen here the case of a greater than b. So for a greater than b, this particular part is your a greater than b is implemented here, whereas a equal to b is implemented with the help of 4 XNOR gates. Okay, whereas following the same logic of your last 2-bit magnitude comparator, you can also implement the a less than b. So you do, I have done it for a greater than b, you do the expression for a equal to b as well as a less than b, and then verify whether you are getting the same circuit or not. Okay, so now let's move on to, so this was all about the magnitude comparators. So we have completed all our magnitude comparator. Now let us move on to the another standard circuit. So the another standard circuit is your decoder. Okay, so up till now we have seen various circuits, and I have first told you the definition of that thing, whatever is that circuit is, and then we have written that logic with the help of truth table, and then by following the K-map and all those things, reducing the expression in the minimum form, we implemented it with the help of logic gates. So this is what the procedure we have followed, and I am continuously repeating it, okay, so that you just remember it, okay, and you can use this later on. So now let's see the decoder circuit. So the decoder circuit, if you just see the definition of a decoder, so decoder is nothing but a circuit that generates all the possible combination of n bits. Okay, so it generates all the mean terms rather. So a circuit which generates all the mean terms corresponding to the n variables, okay, or the n inputs, that circuit is called your decoder. So if there are n inputs, then all the possible combinations of 2 to the power n will be generated by a decoder. So for n inputs, the number of possible combinations will be 2 to the power n. Okay, so then a decoder is specified with like n inputs. So if there are 2 inputs, so for corresponding to the 2 inputs, the output will be 2 to the power 2. So 2 to the power 2 outputs. So you specify the decoder with 2 cross 4. So in some of the cases you will not even you will not find that it is a decoder. Inside the black box it will be written that it is a 2 cross 4. So just by this notation you should understand that it is a decoder. Okay, so it is a 2 cross 4 decoder. Similarly, if there are 3 inputs, then the number of outputs which will be there will be 8. Why? Because 2 to the power 3 is equal to 8. So this circuit generates all the mean terms, or you can say all the possible combinations of this 2 to the power n combinations of n variables, okay, or the n inputs. So this type of circuit is called your decoder. So how to implement it? So let's understand the procedure to design a decoder with the help of a 3 cross 8 decoder. So 3 cross 8 decoder will have 3 inputs. Okay, so 3. So this 3 is nothing but the number of inputs. So 3 inputs. So this 3 inputs can have all the possible combinations as starting from the 0 0 0 up to 1 1 1. So 0 0 0, 0 0 1, 0 1 0, and so on up to 1 1 1. So these are the all 8 possible combinations for this 3 inputs. Now a decoder circuit is a circuit, so these are all the outputs. Okay, and for each of this output, if you want, you can write the K-map to simplify it, but the important thing is how you will write it. So you see this for this particular case, when all the inputs are 0, for this case your D0 should be 1. Okay, but D0 should be 1 only in this case, and it will be 0 for all the other cases. Similarly, D1 will be on only for this case, whereas it will be 0 for all. It will be off for all other cases. Be on for this case, it will be on for this case. Similarly, D2 will be on for only this case. So you see, as if you can see this, then there will be 8 outputs. Okay, for the 8 rows in this particular input side, you will see that for each row correspondingly you will have one output in this outputs. So for this case, if you implement, so you can write the K-map as well, okay, for each of these output to solve, but it is useless to write a K-map because you can see that there is only one out of all this of all these rows in the D0, you can see that only the one is there only in the single row. So there will be, this one row will not combine with any other one. If you write a K-map for D0, then you can just, if you want to simplify it, so it will be nothing but x0, y0, z0. Okay, sorry, x dash, y dash, z dash. Okay, so D0 will be equal to nothing but x dash, y dash, z dash. Similarly, you can write the expressions for any of them. So if you write the expressions for any of them, then you can see that the circuit will nothing but will something look like this. So x, y and z, there are 3 inputs, and if you implement them with the help of this combination, these gates, so D0 is, I have told you, x complement, y complement, z complement. Similarly, your D1 will be x complement, y complement, z. Okay, you can see and you can find that D7 will be equal to x, y and z. And this you use x as well as the x complement. Okay, so to get a complement you use a NOT gate here. So this is how you implement a 3x8 decoder. Okay, so it is a very simple circuit. And if suppose you have to implement a 4x16 decoder, so you have to use accordingly 16 number of AND gates for this, and you have to generate this outputs. So that will be a little complicated to show it here. So that is why we have chosen 3x8 decoder. Now the good thing with this 3x8 decoder, the other application of 3x8 decoder or any decoder can be you can implement any Boolean expression with the help of the decoders, rather than implementing it with the help of our gates, basic gates, derived gates or the universal gates, which we have seen in our last unit. You can implement it also with the help of your decoders. You can implement with them as well, but you can implement any circuit with the help of the decoder as well. Okay, but that decoder should be of sufficient size. So if suppose you want to implement, let's say I'll consider an example that how you can implement any expression, any Boolean expression with the help of decoders. So we'll understand this with the help of a certain example. So the example which we'll consider is, let's say we want to implement this full adder with the help of decoder. So how we will do it? So we'll use decoders and some OR gates. Okay, so OR gates will be required. Other than decoder, you will require just OR gates, a few OR gates. So to implement a full adder, and why you can do this? Because a decoder is going to generate all your mean terms. So if once all your mean terms are generated, and as you know from your earlier discussion, that the expression, any expression can be written in terms of mean terms, and if these mean terms are available, then you have to just OR them to get the expression. So then that is why the decoder is useful. So you see, for some expression for full adder, if you remember from your previous discussion, then you will find that the expression for sum will be this sum of mean terms of this mean terms 1, 2, 4 and 7, whereas the carry output will be the sum of this mean terms 3, 5, 6 and 7. So if you take a 3x8 decoder, because you see these outputs are going, if you see the maximum mean term, the decimal equivalent of the maximum mean term, so you can find that it is 7. So 2 to the power 3, if you see, so 2 to the power 3 should be greater than this maximum value. Okay, so maximum mean term present in the expression. So you can see that if you use 2 to the power 3, which is equal to 8, then this mean term is 2 to the power 3 is greater than this 7. So that is why this decoder, 3x8 decoder, will be used to implement this expression, which have mean term as just less than 2 to the power 3, okay, or 2 to the power the number of output should be greater than this. So you see the decoder you have chosen is 3x8 decoder. Now this decoder will, inside it you know what should be there, so we have discussed it already. So from here I am just writing the output, the decimal equivalents of the output, whatever I'll get. So the mean terms which will be available at this output will be 0. The mean term which is available at this output will be 7. Okay. So inside it what is there, we have already seen it. Now if you have all the mean terms available, then the sum expression will be nothing but the sum of these mean terms 1, 2, 4, 7. So you take the output from this 1, then 2, then 4 and then 7, and you combine them together with an OR gate. So this is your sum output. Okay. Similarly, to obtain the carry output, what we do is we combine the mean terms corresponding to this expression. So it is nothing but 3, 5, 6 and 7. So we combine them with an OR gate, and we see that this is how we obtain an OR gate, this carry output. So this expression, you can check, you can verify it either in simulation or in the hardware with the help of decoder. If decoder is available, then this circuit will give you a full adder. Okay, so you can implement a full adder with the help of this decoders and this thing, OR gates. So this is the way. So we have seen the one of the applications of this decoder. Then the other application of decoder is, suppose you have a certain lower order decoder and you want to realize a higher order decoder. So that is also possible with the help of this decoders. So let's say you have the 3x8 decoder is available to you, and you want to implement the application wants a 4x16 decoder. So how to implement a 4x16 decoder with the help of 3x8 decoder? Okay, so to implement this type of decoder, what we will see is this logic. So the logic is this particular decoder. In the earlier this discussion, I have told you the decoder, but that decoder was without the enable input. But here, if you want to implement the higher order decoder with the help of lower order decoder, then we have to use a decoder with an enable input. So what does this enable input signifies? This enable input just signifies that this particular circuit will be active when this enable is 1. Okay, so this type of logic is called enable, means active. Okay, so active high circuit. So whenever this enable is 1, so this circuit will become activate. This circuit will get activated. So now you see, if you have if you want to implement a 4x16 decoder, then what we will do is there are 4 inputs. So 3 of the inputs are common to both the decoders, but one of the input we have applied to the enable input. Okay, so this enable input to one of the decoder we have applied just the this 4th bit, whereas this 4th variable, whereas the complement of this variable is applied to the another decoder. So what will happen with this? The thing which will happen with is will be like, if when A3 is equal to 1, so this upper decoder will get activated and it will generate this circuit. Okay, whereas when A3 is equal to 0, then this, you see, if we are using an inverter, so this will become 1. So this will become 1, and here this circuit will get, this lower decoder will get enabled. And when this A3 is equal to 0, so the lower circuit is enabled and it will generate the terms from Y0 to Y7. Whereas when this decoder is enabled, then it will generate the terms from Y8 to Y15. So if you will check it, you will find that you are getting all the 16 possible combinations. So overall, you should have 4 inputs and the 16 output in a 4x16 decoder, and you can see that you will get this particular by the help of 3x8 decoders. We implement 4x16 decoder in this way. Okay. Now moving on to the another decoder, which is called as BCD to 7 segment decoder. So a BCD to 7 segment decoder, what we do in this BCD to 7 segment decoder, we want to display a certain BCD number, okay, on this 7 segment. We want to display this number, and to display this number, the thing which we use is called a 7 segment display. So why this is called 7 segment? Because there are 7 segments in this particular section. So you can see there are 7 sections: A, B, C, D, E, F and G. Okay, so this is in standard practice to mark them as like this from A to G, and this have like 7 segments, and it can be used to represent any digit. Okay, so that is why it is called this particular type of display is used to represent any digits. Okay, in the on the railway stations and in the digital watches, you may have seen this 7 segment display. So this 7 segment display, how to show any digit, okay, starting from 0 to 9, how to display it on the 7 segment display. So that type of decoder is called your particular BCD to 7 segment decoder. So we have a BCD number which is from 0 to 9. So a BCD number can have values from 0 to 9. So that BCD number will convert it and will show it on the display. So how to do that? To do that, we will use a 7-segment display, as I was telling you. That 7-segment display is nothing but it has certain LEDs. So some LEDs which shows which displays they are red color LEDs, or you can make it with the any other color LEDs as well. Okay, so these LEDs will have some inputs. So this A, B, C, D, E, F, G, whatever you can see will be these LEDs. Okay, so these LEDs A, B, C, D, E, F, G, and this LEDs the inputs to these LEDs are given here, and one of the terminals of this LEDs is common. So here in this case, if your this ground is common, then this is one type of combination. So this is called common cathode type of display. Okay, whereas the other type of display, you can this display can be of two types. So that is what I mean. So that can be of common cathode type display, or it can be a common anode type display. So common anode type display, what happens? This all the all the terminals of this the other diodes, these positive terminals are connected together, whereas the negative terminals are like open. So we'll see that they are connected to either of them. Okay, so how to make a circuit which can convert a BCD number to this LCD which can display on it. Okay, so 7-segment decoder. So we have to implement a circuit which is called as BCD to 7-segment decoder. Okay, so how to implement it? So to implement it, first of all, the very first step is we have to write the truth table. So we have a number in BCD which is written from 0 to 9. So you can check it. These are the input lines. Whereas in the output, you will see that there are 7 segments. So for each segment, I have written the output. So now you can see from your previous discussion, not from the previous discussion, just from observation, if you see that if this is your 7-segment display, so then to display 0 on this 7-segment, what you have to do is you just don't display this G. So this G should not get the supply. So if you consider here in this circuit, this should be off, whereas all these other LEDs should be on. Okay, whereas if you want to display 1 by this LED by this 7-segment, then this just B and C should get the should these two LEDs should be on. So this the supply should come only to this LEDs, whereas to the other LEDs they should be off. So you see, in this case, if you consider it a common cathode type of display, so then the display the output, the input will be only to B and C LED, so these two LEDs, whereas the other LEDs will be off. So how to do this? Okay, that how, some LEDs will be on and some LEDs will be off. So how to do this arrangement? So to do it, what you do, you write a truth table, and from this truth table you can verify that in case of G, as I have told you, the 0 is for G. If you will see the truth table, then you will find that for to display 0, okay, so all other LEDs are on, whereas G is 0. Okay, so this is how you see. To display 1, I already told you that B and C will be 1, will get 1, whereas other inputs whereas the other output should be 0. Similarly, to display 2, you can see the display, the 2 will look like something like this. So your display will be A, B, G, and the other displays you can check the numbers. Okay, so A, B, G, and E and D. So you can see this A, B, G, E and D. So A, B, D, E and G. So this are coming, they are becoming 1. So this way you have to write the truth table, and if you write the truth table for each of these output, okay, so once you write this, complete this truth table, then you just pick one of the output. So let's say if you pick G, so then you will realize the output for you write the K-map for this G, okay, and then fill up all these entries, okay, and it will be a 4 variable K-map, okay, because you see there are 4 variables on the input side. So let's say if I write the variable, if I write the K-map for variable A, then the K-map will look like something like this. And if we form the proper groups, okay, then the expression for A will be something like this, okay. Whereas for C, B I have not written. You can try it. I have shown you 2 outputs, that how to write the K-map for 2 outputs. You can check its grouping and all the things, okay. And if you find any mistake, you just point me out as usual. But if you don't find any mistake and if you find it useful, try to implement it for all the other outputs, because if it comes in question, then you have to apply, you have to show the K-map for each of these output, okay, if somebody asks you in the exam. So you just practice it once. So these are all the outputs. So then you write the K-map for each of the output, and write decay maps, simplify them, get the expression, and after getting the expression you draw its hardware. So you can verify the hardware for A and C. So the expression for C is looking simple, so I'll show this. So C is equal to B plus C complement plus D. So C, small c is equal to B plus C complement plus D. So how to see this? So C want to implement, so you can verify it, it is, so you can just verify from this. So it is difficult to verify. So again I have taken, I mean, in this slide you can see that it is I have taken it from electrical technology org. In the previous slide also I have shown you. So this diagram is taken from there. Although some of the diagrams I have taken from some websites, but I have just missed to show it, just to inform you that, okay, refer them. But I have taken some diagrams in this particular presentations I should say, from some websites. Okay, so because they were difficult to draw and I was a little lazy, so I have just copied them from there. I'm sorry for that, but I will like to have get your help on this particular things. Okay, so I'll stop this particular lecture here itself because my battery is also getting low. It is continuously showing me the signal, and the next topic is like the new topic, the new hardware, the new the circuit for the new circuit. So we'll see it in the next class. Thank you for listening this part. Thank you.